Namaskar. I am Rudra Kafle from Worcester, Massachusetts. This is Physics is Fun, Episode 10. Okay, so today we are applying Newton's laws of motion in circular motion. Okay, as I informed yesterday in my video that we will be doing circular motion. Okay, which is a kind of interesting and important kind of motion. Right? For example, a car moving in a curve, a circular track, circular path, right? Similarly, planets going around the sun, okay, or the moon going around the planets, right? These kind of motions are circular motions, okay? So here, how can we apply Newton's laws of motion? Okay, that's the topic of today, okay? So let me do a couple of quick demonstration, okay? So I have this ball, okay, foam ball tied to a string, okay? So what I do is I move this in a circular path, okay? What do I do? So I can move like this way, right? Which makes this ball makes a horizontal circle like this. Okay, or I can move like this in a vertical circle like this. Okay, so the ball is now making a vertical circle like this. Okay, so now let's try to understand. This is a very simple demonstration, but how Newton's law of motion work here. Okay, so what I am doing here is I am moving this way. Okay, before that, let me start. When I suspend the ball, right, to this string, using this string, right? So let's try to understand how many forces are acting on the ball. Okay, please think for a couple of seconds. How many forces? Okay, probably you thought about that. Okay, you can also discuss with your friend or parents or seniors, whoever around you. Okay, you can share your idea. So there are two forces, right? One is the weight, gravitational force, which is vertically downward, right? Other is the tension force, right? The force string is acting on this object vertically upward, right? So I am holding it, but I am not directly touching the ball. So I am not directly applying the force on the ball. That's very important. Sometimes we are confused. Since I am holding, so probably am I applying the force on the ball? That's incorrect, because I am not touching the ball, right? I am holding the string, right? I am holding the string, and the string has a force called tension upward, weight is downward, right? So tension is upward, that is one force, right? Gravity is downward, which is m times acceleration due to gravity at this place. Okay, there are two forces. By the way, if you draw a block, simple, let's say rectangular block, right, and then show those two forces, mg vertically downward and tension vertically upward, right? So the object is not moving, the object is at equilibrium now. So those two forces add up to give zero. From Newton's second law of motion, F equal to ma, this object has no acceleration, it is in equilibrium, so acceleration is equal to zero, tension is upward, mg is downward. So set up a proper coordinate system. If upward is positive, downward is negative. So T is the tension, let's say, mg is the weight, so T minus mg equal to 0. So this shows that tension equal to mg. So how much tension on this string? That is mass times acceleration due to gravity. You can measure the mass of this ball. Acceleration due to gravity on Earth's surface on the average is about 9.8. Multiply that. That is the tension on this. Okay. Hopefully this makes sense to you. Okay. So it is in equilibrium. And let me also introduce a new terminology here. So you drew a block, right? And tension is vertically upward, acting on the object, right? On this ball, right? mg, that is the weight of this object, is vertically downward, and that kind of diagram is called force diagram or free body diagrams. these are extremely important. These are extremely important diagrams, or this is extremely important concept to solve problems, right? So I am always telling a kind of concepts to you, but you need to apply these concepts to solve problems, okay? Otherwise, your learning will not be complete, okay? So we knew that at equilibrium there are two forces, right? Two forces. One force is vertically upward, which is tension. The other force is vertically downward, which is weight. So those two forces are equal, and so they balance. Now, when I start rotating, moving in a circle like this, still there are two forces. Still there are two forces. One is, of course, tension, right? And the other one is weight, right? But now they are acting in a slightly different direction. No matter whatever way it moves, weight is vertically downward always. Weight is always vertically downward. But once it makes a kind of slant like this, so tension is along the string, okay? So what will happen is, when you consider the tension along the string, you can split, tension is the force, you can split into horizontal component and vertical component, okay? Because tension is the force is vector, it has components. One component is that way towards the center of the circle, other component is vertically upward. So the vertically upward, so it is not moving vertically up and down, it is not accelerating that way. So again, the vertical component of the tension and the weight, they will neutralize each other, they balance each other. But the horizontal component will provide what we call is the centripetal force. So this is a new term for you. Let me repeat this sentence. The horizontal component of tension provides the centripetal acceleration. That means, see, when this object moves in a circle, this object moves in a circle, there is of course acceleration. Why? What is acceleration? Acceleration is the change in velocity divided by time. So suppose even if I move at constant speed, the velocity is changing. Why? Because the direction changes. Whenever the ball is around here, maybe velocity is that way, tangential to the circular path, here that way, and here that way, and here this way. So the direction is continuously changing. So even if the speed is constant, velocity is not constant, direction is changing. And if you draw a diagram very carefully, the acceleration is toward the center of the circular path, okay, center of the circle, okay, center of the circle made by this ball, okay, that is called centripetal acceleration, okay. Now we apply Newton's second law of motion, and that is very interesting, right? So what happens in the vertical direction, the tension component of the tension in vertical direction, when it is something like this in a circle, right, the component of tension in vertical direction balances the weight, right? Okay, that balances the weight. But what will happen to the horizontal component, right? There is, for example, if you consider this angle to be theta, for example, this angle to be theta, right? So t cosine theta, right? Some trigonometry there, t cosine theta equal to mg, right? And then other component t sine theta, I am using trigonometric function t sine theta equal to this gives the centripetal acceleration, because there is no other force to balance in there. By the way, there might be small amount of frictional drag, air drag, so that part I have neglected here, okay, that part I have neglected here. So the t sine theta, that is the force in that direction, equal to ma, right? F equal to ma, that is Newton's second law of motion, right? Okay, so that component of the force causes acceleration in that direction. And so, by the way, interestingly, that acceleration is always toward the center of the circle. If I can give the constant speed, if I can give a constant speed, that will be always toward the center of the circular path. For example, if you consider a satellite or a planet, consider a planet going around the sun, right? So what is the force between the planet and the sun? Please think about for a second. So when a planet goes around the sun, right? When a planet goes around the sun, okay, so when a planet goes around the sun, so what is the force between the planet and the sun? We know that is gravitational force given by Newton's law of gravitation. Okay, the force equal to is proportional to product of masses If the mass is larger, force is more, and inversely proportional to the square of the distance. Larger the distance, force will be less, and by the way, it goes by the square of the distance. Okay? And there is a constant which we call universal gravitational constant. Okay? But we need to be very careful. The orbit of the planets are not always circular. Okay? So they are usually elliptical orbits. Okay? They are like ellipse, like oval, like egg shaped. Okay? If you take the projection of the egg on a plane, so you will get a kind of oval shape. Okay? So in that case, we need to pay extra attention. Let's not go that far today, right? So in the circular path like this, right? In the circular path like this, right? So the tension, the component of the tension on the string provides the centripetal acceleration, which is in my example, t sine theta is equal to m times acceleration. And very interestingly, acceleration is related to the radius of the circle. The object follows how big is the circle and the radius of the circle and acceleration. Acceleration depends upon the speed, how fast is the speed and the radius of the circle. I will show you that mathematics in a minute. Okay? Okay? So now let's consider a slightly different kind. Right? Let me do this motion of this object in a vertical circle. Like vertical circle, like this. It is going up and down in a vertical circle. Right? Like this. It is in a vertical circle. May not be perfectly vertical. Right? But you can do once you practice for a while. Right? So in a vertical circle. So when it goes in a vertical circle, again, on this object, there are two forces. One is the weight of this object, and the other one is tension. Right? But in the vertical circle, we need to be careful, right? We need to be careful. What is that? So in the horizontal circle, tension is always along the string that way at some angle, and weight is always downward. But if you consider the vertical circle, right, weight is always downward no matter what. Weight is always downward, mg is always downward. But the tension, like say, when it is here, tension is upward. When it is here, tension is horizontal along the string. When it is here, tension is downward. When it is here, tension is to my left, right? So tension, the direction of the tension continuously changes, right? And so if this moves without forming a slack like this, right? If this becomes taut, right, in a vertical circle, right, you need to give a minimum amount of velocity. Okay, how much is that velocity? I will show you, right? And that is what is called the critical velocity or the minimum velocity in the vertical circle. Okay, now let me show you some very, very interesting example. Okay, I would like to alert on this experiment. So if you are children, so if you do this experiment, please take help of your seniors or your teachers. If you are teachers and you want to do this demonstration in classroom, please pay extra attention for safety. Okay, so what I am doing is I have a water bottle. Probably you see it has water, and then I have taken off the lid. Okay, you can see. I can pour water. You trust me, but just to make sure that, like, so I have taken the lid off. Like you see, I am pouring water. Right. So this bottle has water. Right, halfway filled. Okay, so the distance from here to about the midpoint is about 25 centimeters, right? So what I am doing is I am moving this water bottle in vertical circle, okay? I am moving this water bottle in vertical circle. So now, see, the mouth of the bottle is facing upward, water is in the bottle, we are safe. Now if I tilt, of course, up to certain point, the water doesn't spill. But if I make upside down, right, so water is fluid, and because of gravity, it flows downward, so water spills, right? But what I do is, I move such a way that I give a certain amount of velocity so that water does not spill. Okay, let me show you. Okay, let me show you this. Okay, let me show you this. Okay, let me try. But again, if you do this experiment, if you try to do this kind of experiment at home, if you are children, please take help of your parents or seniors, and if you are teachers, please pay extra safety, extra attention for safety in the classroom. Okay, so let me do this. Okay, let me do this. I have practiced this morning, so I should be good. I should not spill water. Okay, right? So you see, so I am moving this in vertical circle. You see that? So at some point it is upside down, but water is not spilling. I am good, right? So water is not spilling. So what is happening there? Again, we can explain that by using Newton's second law of motion. Now, you may raise a question. So the mouth of the water bottle was small, right? So because of that, water is not falling, right? We can ask that kind of question. But that is not right. Even if you use a bucket, okay, again, if you use bucket, please pay extra safety. How strong is the handle? Okay, how much water you put? So I cannot do that experiment in this small environment in the room, but I have done this experiment outside. Okay, let me show you a quick video. Okay, let me show you a quick video to you. Okay, 1 second. So I am showing a quick video to you on this. Okay, so you see my YouTube video setting. I have not played, so please watch and try to listen to me what I am saying and what I am doing. Okay, please. I play couple of times, so please watch. So here is water in the bucket. Now I move the bucket in the vertical circle. The water does not spill out even if the bucket is upside down. See? Why? Because the weight of the water just provides the centripetal force required to move in the vertical circle. Okay. I hope you saw that. So let me play one more time. So here is water in the bucket. Now I move the bucket in the vertical circle. The water does not spill out even if the bucket is upside down. See? Why? Because the weight of the water just provides the centripetal force required to move in the vertical circle. Okay, so probably you heard that brief explanation, right? You saw there was water in a bucket. Its mouth was wide open, not like a small mouth of that a bottle, right? There was water. So I was moving that safely in a vertical circle. Okay, so how can that be explained? Okay, how can that be explained? So let me explain that to you. Okay, so let me explain that to you using some mathematics. Okay, so you see my screen. What I have written is Newton's second law of motion. So that equation is by now you are familiar with this, right? You are very familiar with that. F equal to ma. And please don't forget the arrow on top of force and on top of acceleration. Okay, F equal to ma, where m is the mass of the object, a is the acceleration, and F is the net force, the total force. Okay, and force and acceleration are vector quantities. They have both magnitude and directions, but m is the mass, which is in kilograms or grams. Mostly we use in kilograms. We use all in SI unit, right? But in circular motion, we write this way. In circular motion, now mass is mass, but acceleration now I have replaced with v square over r. What are those quantities? V is the magnitude of the velocity, or you can call it speed, right? Speed squared, and r is the radius of the circle. It doesn't matter whether you consider a vertical circle or horizontal circle, that is the radius. Okay, right? But the dynamics are a little bit different. We need to be careful. Okay, so r is the radius of the circle, v is the speed, and I have written unit vector r hat to show that force is vector quantity. The quantity in the parenthesis is what we call centripetal acceleration. Okay, centripetal acceleration. Okay, and that centripetal acceleration should be provided by some force. Okay, so for example, in the horizontal circle, right, when we consider a ball and a string, a component of tension provided that centripetal acceleration, right? In the vertical circle, right, again there are two things, like in case of ball and string, tension and the weight. But in case of water, right, if you consider water bucket, so weight of water is vertically downward, but water is being pushed by the bottom of the bucket, which is what we call reaction force. Okay, so now, so for water not to spill, as I demonstrated that water did not spill, for that what we need to do is that acceleration must be equal to acceleration due to gravity, right? F equal to ma, right? So instead of F, I wrote m times z. That is mg is what? Mg is the weight, right? Is equal to m times acceleration. That is Newton's second law of motion. So if I cancel m from both sides, right, then I get the critical velocity square root of r times z. Okay, square root r times z. Okay, so what I did that, so for the water in the bucket or in the bottle not to spill, you must give the velocity which is square root of r, radius of the circle. You want to intend the bottle or the water to go to rotate in the circle, and z is the acceleration due to gravity. And I have done a small calculation in my example. So what did I do in my water bottle? In my water bottle, the distance, as I mentioned, was the radius was about 0.25 25 centimeter, which is 0.25 meters, and z is 9.8. So for that, I must have moved that bottle at 1.57 meter per second. If I move with a speed smaller than that, what will happen? Water will spill, right? So that must be, at least that speed should be given to me. But in everyday life, it is very difficult to measure the speed. So let's do something else. So we can calculate how much is the time for one complete circle. Okay. So corresponding to that speed, if you calculate the time, right? So from simple equation, time is equal to 2 pi r, which is the circumference of the circle, right? That is the circumference of the circle divided by the speed. So that comes in my experiment, that comes to be about 1 second. So what does that mean? What does that mean? So what does that mean is this. So my water bottle here, right? If when it makes a circle, okay, let me do one more time, right? So if it makes a circle, if I can time like at least 1 second going in a vertical circle, then I am safe, right? Water will not spill. Okay, if it goes slower than that, so what will happen? Right? So will water spill or not? If it goes faster than that, what will happen? So these are the questions to think about. Okay, please think about this question. And one more question. So I am going to stop this session today, leaving one question to you. The question is something like this. Okay, the question is something like this. Please think about this question. Okay, so here, this ball, I am moving in a circular path. So what I am going is I am increasing the speed. Okay, I am increasing the speed faster and faster and faster and faster and faster and faster, right? So in the beginning, it was something like this. That is called conical pendulum. By the way, it forms a kind of pendulum called conical pendulum. Okay, but when I move faster and faster, so what happens? This becomes more horizontal and horizontal and horizontal. But can you in the Earth's field, Earth's gravitational field, that means while we are sitting on the Earth, can you move this ball in a perfect horizontal circle, right? Can you move, like go on increasing the speed faster and faster and faster and faster? Can you make this ball to move in a perfect horizontal circle so that the string and the ball lie on a horizontal plane? Okay, this is a very important conceptual question. Please think about this. Okay, that is one question for you. Okay, and the next question is, so as I mentioned, like, so when you drive in a car, suppose you do cycling or you drive a car or you drive a motorcycle, right? So in a curve, right? So what factors provides the centripetal acceleration, right? What factor, what is the force there in a curve which provides the centripetal force, right? So when a pilot flies a plane, so takes a kind of bank, like so when a pilot tries to turn in air, right? What factor provides the centripetal acceleration? Okay, and also when the planets go around the sun, right? So in a highly elliptical path, what is the actual direction of acceleration? It is exactly toward the sun or different. So these are the questions to think about. Okay, so please think about these questions seriously. You can search answers in the internet or some reliable sources in the internet or some textbooks. Okay, so please think about this, and we will definitely meet next time. So thank you so much for coming to my live session. I hope you learned something. Okay, so please write some comments, give me feedback. Okay, so how helpful is the session? How can I do better for you? How can I improve the session? With that, I would like to stop this video. Thank you very much and have a nice day.